Assalamualaikum sir. Welcome to my power system operation and control case study presentation. Sir, I am Muhammad Rakhi Parvez, roll 436769 CBS, Department of Electrical and Electronics Engineering, All University of Bangladesh. Submitted to Dr. Muhammad Mohsin sir, Assistant Professor, Department of Electrical and Electronics Engineering, All University of Bangladesh. Now I start the case study presentation. First, see the list of content. Here see the wall content title and page number. Then figure list, equation list and mathematics list. Then see the first page. Load forecasting. The estimation of load is advanced is commonly known as load forecasting. It is necessary for power system operation purpose of load forecasting. 1. For proper planning of power system. 2. For proper planning of transmission and distribution facility. 3. For proper power system operation. 4. For proper financing. 5. For proper manpower development. 6. For proper grid formation. 7. For proper electrical cells. And the wall load forecasting keyword shown here. Then classification of load forecasting. The load forecasting can be classified as demand forecasting and energy forecasting. Forecasting procedure in short term, medium term and long term. Then characteristic of power generation unit. Here we see the steam power generation system. First boiler, then turbine and last and finally generator. The generator output is electrical power and the turbine output is mechanical power. Then we see the system variable. To analyze the power system network, there is a need of knowing the system variable. There are control variable, distribution variable and state variable. Optimum dispatch formula. Let us see the optimum dispatch formation. Input output characteristic, cost curve. To convert the input output curve into cost curve, the fuel input per hour is multiplied with the cost of the fuel. Incremental fuel cost curve. The incremental fuel cost equal del input by del output. The IFC or incremental fuel cost is known obtained as SIC equal slope of the fuel cost curve. Then we see the fuel cost curve 1 and 2 and some equation. Then see the heat rate curve. The heat rate curve is increasing cost curve. Incremental efficiency. The reciprocal of the incremental fuel rate or heat rate, which is defined as the ratio of output energy to input energy given a measure of fuel efficiency for the input. Mathematical determination of optimal allocation of total load among different units. And there is the mathematical term and important equation. The cost of I unit is given by the following equation. Ci equal 1 by 2 AI PGI square plus BI PGI plus DI. Then we see the problem and solution. Problem 1, problem 2 and problem 3 and the solution. Now we see the unit commitment. The total load of the power system depends upon the consumer. It taken different peak value throughout the day. The number of running generating unit depend upon the value of total load of that particular time. Unit commitment UC is a computation process to select a running generator unit the advance for the particular time in a day. And necessary of unit commitment has the necessary 1, 4, 2 and 3, 4. Then factor affecting unit commitment. There are many constants to the consider in solving the unit commitment problem. 1. Spinning reverse to thermal unit constants, minimum uptime, minimum downtime and crew constants. 3. Hydro constants. 4. Must run unit. 5. Fuel constants. Additional discussion: spinning reverse, shut up constants, then computation process of unit commitment. Let Fi be the cost of operation of the I unit, Pgi the output of the I unit, and Ci the running cost of the I unit. Then Fi equal Ci Pgi. And the sum formula and equation. Then example 4 and our solution. The important equation: the cost of I unit is given by the following equation: Ci equal 1/2 Ai Pgi square plus Bi Pgi square plus Di. Then Pg1 equal lambda minus B1 by A1. Pg2 equal lambda minus B2 by A2. Pg3 equal lambda minus B3 by A3. And the calculation table on. Then the simple peak value load pattern figure. Unit commitment operation of simple peak value load pattern. Shutdown rule. Let us assume that the load following a simple peak value pattern as shown in figure 1. The up figure. To optimization the system operation, some unit must be shut down as the load decreases and is then the recommencing as it goes back up. And you see the table 2 and a figure. Unit commitment schedule using the shutdown rule figure. And priority list method. The list method is some equation and problem solution. And load frequency control. Active power demand and reactive power demand are always changing. Active power demand has been controlled by prime mover in a generating unit. Reactive power demand has been controlled by the execution system of the generating unit. Frequency in a power system must be controlled within ±2% variation. Necessity of maintaining frequency constant. Constant frequency is to be maintained for the following formation. The formation is here. And load frequency control. Load frequency control LFC is the basic control mechanism in the power system operation. However, there is a variation in load demand on a generating unit. There is momentarily an occurs of unbalance between real power input and output. This difference is being supplied by the strong energy of the rotating part of the unit. The kinetic energy of any unit is given by Ke equal 1 by 2 I omega square. I is momentum of earth of the rotating part and omega is angular speed of rotating part. The governor characteristic. Governor sensor the change in a speed control mechanism to adjust the opening to steam value in the cost of steam turbine and the opening of water gates in the case of water turbine. The characteristic of typical governor of a steam turbine are shown figure 1, which is linearized by dotted line for studying the system behavior. And see the characteristic typical governor. The steady state speed regulation in per unit is given by R equal n naught minus n by n. N naught is speed at no load and n is speed at related load. The value of R varies from 2% to 6% for any generating unit. Seeing the frequency and speed are direction related, the speed regulation can also be expressed as the ratio of the change in frequency from no load to its full load to the related frequency of the unit. R equal f naught minus f by f. And figure is speed governors skating. Then PF control. The load frequency control, also known as generating control, or PF control. The control of loading of the generating unit for the system at normal frequency. The load in a power system is never constant and the system frequency remains at its normal value only when there is a match between the active power generation and the active power demand. During the period of load change, the derivation from the normal frequency, which may be called frequency error, del f, is an index of mismatch and can be used to send the appropriate command to change the generating by adjusting the load frequency control system. And QV control. In this control, the terminal voltage of the generator is changed and converted into proportional DC signal, and the compared to DC reference voltage, the error in between a DC signal and a DC reference voltage. Then we see the generator control PF and GV. Then we see the generator controls PF and QV controls. The figure. Speed governor system. The speed governor is the main primer tool for the load frequency control. The mechanic is used along to feed a small system, or it is a part of the most elaborate arrangement. A schematic arrangement of the main feature of a speed governor system. of the kind used to steam turbine to control the output of the generator to maintain cost frequency is as shown in figure. Its main part or component are following as flywheel, speed governor, hydraulic amplifier, speed changer, and linkage mechanism. Speed governor system figure, then solving equation, example 5 and the solved solution, and example 6 are solution, and example 7 and her solution. Then system security. The security control or a security control system may be defined as a system of integrated automatic and manual control for the maintenance of electronic power service under both normal and abnormal condition of operation. To keep system always secure, it is necessary to perform a number of security related studies which can be grounded into three major areas, namely long-term planning, operational planning, and online planning. Long-term planning. Evaluation of generation capacity requirement. Evaluation of transmission system accuracy. Evaluation in interconnected system power exchange capability. Operational planning. Determination of spinning reverse requirement in the unit commitment process. Scheduling of hourly generation as well as interchange scheduling among system. Outage dispatches of transmission line and transformation for maintenance and system operation. Online operation. Monitoring and estimation of the operation state of a system. Evaluation of steady state transmitted and dynamic security. Quantitative assessment of security index security achievement through constant operation. Security analysis. Security analysis is a determination of the security of the system based on a next continuity set. This involves verifying the exchange and normally of the past contingency state. If all the post contingency state exist and are found to be normal, be state of secure. On the other hand, the non-existence of event one of the post contingency state or emergency nature of an existing post contingency state indicate that the current state is insure. Now we end my case study. Assalamu alaikum sir. Thank you.